Hello everyone. In this video we're going to look at how we can derive composite functions using something called the chain rule. So let's suppose we have y equals f at v. So y is some function of v, which is another function. And v is a function of x, as defined here as g of x. So in other words, y equals f at g of x, or written another way, f at g of x. So we have a composite function. The chain rule basically tells us that the derivative of y with respect to x, now remember, we've generally been deriving with respect to x because x is our independent variable. But actually, we could switch this around. We could find dx dy if we wanted the vertical change over the horizontal change over the vertical change. If we weren't really focused on slope, we could switch it around. If I have an equation that is, let's say, distance as a function of time, then when I take my derivative, I'm finding the derivative of distance. That's a little confusing, but with respect to time. So our variables are fluid here. So if I'm wanting to know what is the derivative of y with respect to x, so dy dx, I can first derive y with respect to v, and then dv dx, and it will simplify exactly as we would expect fractions to simplify. Or expressed in the Newton notation, f prime of x equals f prime of v times g prime of x. So that becomes a little clearer when we actually start to see it in action, what that notation means. So let's say we're starting off with y equals 7x squared plus 9x minus 2 all to the power of 5. Now technically we could derive this using just the derivatives of polynomials if we were to actually multiply out 7x squared plus 9x minus 2 5 times. That is quite inefficient, but it would get us there. The chain rule basically saves us that work. It says, look, in this case, I have y is some function of v, and that basic outer function here is raising something to the power of 5. That's the exterior function here. Inside of that raising it to the power of 5, I have another function, and we'll call that v. So v is 7x squared plus 9x minus 2. That's what's being raised to the power of 5. Now, if I consider dy dv, well, that's simply going to be 5v to the power of 4. And dv dx, well, that's 14x plus 9. Now, according to this chain rule, then, dy dx is going to be 5v to the power of 4 times 14x plus 9. But we don't actually have v, so I'm going to replace v with the expression for x. So 5 times 7x squared plus 9x minus 2 to the power of 4 times 14x plus 9. So the overall derivative, I derive the outside function, so to the power of 5 becomes 5 times that thing to the power of 4, and then I have to multiply by the derivative of whatever was inside the brackets. That's essentially it. That's the chain rule. So let's look at that in a few more examples. So starting off here, f of x equals, all right, I'm going to write this as a power. So 5x plus 8 to the power of 1/3. So the outside function is to the power of 1/3. So the derivative of f with respect to x. First, I'm going to ignore the 5x plus 8 and just pretend it's a single thing. So this becomes 1/3 times 5x plus 8 to the power of negative 2/3, just by applying the power rule there. But now I have to multiply it by the derivative of what is inside, by 5x plus 8. So the derivative of 5x plus 8 is simply 5. Now cleaning this up a little, I get 5 over 3 times 5x plus 8 to the power of 2/3. If I think of what the chain rule was in Newtonian notation, f prime of v, well, if I just pretend that v equals 5x plus 8, then f of v simply is v to the power of 1/3. So f prime of v is 1 over 3v to the 2/3. And then v being 5x plus 8, I'm going to call that g of x, g prime of x is therefore just 5. So when I substitute that into the chain rule, which said that f prime of x is equal to f prime of v times g prime of x, we get 1 over 3v to the 2/3 times 5, which when we replace v with 5x plus 8 is exactly what we just had in the previous example. What I've written in green is not work you would have to show, but it does sort of explain how that notation works. Let's do one more example together where we are wanting to find dy dx, and I'll show sort of the minimum amount of work I would have to do to solve this question. I'm going to start by writing it as a power. So this is -2 times x cubed plus 5x plus 1 to the power of -3. So dy dx, I'm going to start by deriving the power because that is the outside function. So -2 times -3 becomes 6. And the new power here, I have x to the power of 3 plus 5x plus 1 raised now to the power of -4. So I've just derived the exponent, essentially, part of this function, but now I have to derive the polynomial that is inside the brackets, and that is 3x squared plus 5. Tidying that up a little, I get 6 times 3x squared plus 5, all divided by x cubed plus 5x plus 1 to the power of 4. And there we go. There's the derivative.